there was mentioned I was a PhD student, but what we're really looking at was how do we integrate human systems integration ultimately into a shipboard environment. And doing the slide thing here. Why? Because 2017 was a really rough time for the US Navy. And while we talk about the US Navy, there's not a service out there within the Department of Defense that hasn't had similar difficulties. Out in the Pacific Theater, there were 3 collisions and a grounding, resulting in combined loss of 17 sailors. Out of that, the Fleet Forces Memorandum, 26 October, talked about the fact that the Navy needed to invest itself into taking a look at the objective measures of human and unit performance. And agent-based modeling, particularly what I learned through my use of AnyLogic and object-oriented simulation, really would benefit the Navy's look at these kind of things. It so happened my work was going on in tandem with what was going on in the Navy within the 2017 environment, but they meshed together very nicely and provided a perfect example of why we were looking at that human system integration into the Department of Defense complexes. The time variance in humans, time variability in humans, plays a key role in those time-critical situations. There's multiple out there. There's nuclear reactor operations, there's air traffic control, and then there's ultimately the Department of Defense and their battleship operations from that perspective. And I could pick anyone in the audience and say, I'm going to race you out to the corner. And during that race, we would have undoubtedly 2 different time variances of the way we're going to perform that race. And even better, if we could come back tomorrow, you may perform better or worse, and I may do the same. Not only do you have the intervariability in humans between you and me, but you have the way that I'm going to perform today versus the way I'll perform tomorrow. Maybe I won't feel as well. Maybe I'll stub my toe tonight and have a hobble. It's hard to say. So how do you take a look at that variability and that time and understand how that is going to affect your overall ability to fight the ship, or even in the case of this, to be able to react efficiently and effectively to other ships at sea to preclude the loss of the human lives and obviously the damage to the equipment. So this was an effort to look at that human systems integration, to understand the crew variability, and then to identify how that actually affects Department of Defense applications. So you see the variability in this one underneath the objective, the visual depiction, on the timelines and the variance and the human performance. And how do you predict that across multiple tasks, multiple efforts that sailors are going to perform in order to, like I said, fight the battleship or to maneuver the ship appropriately and timely to avoid a collision and the resultant damage. So that was the ultimate look. And then one of the things we wanted to take a look at was to demonstrate the utility and extensibility. And we chose to do with that, and this was basically driven by the data we had, was we chose to look at the small boat defense scenario. In other words, swarming or a small boat approaches a battleship, as has been seen the case, and that was the resultant of the damage on the battleship that was on the front page, on the front cover of the presentation. So from that perspective, how do you take a look at how that affects it and what's the ultimate impact to the sailors overall and the ship? So why did we look at AnyLogic? Well, one, mine was completely agent-based. My effort was completely agent-based from a research perspective. But that extensibility and the utility is you have the ability to go into a multi-method modeling capability where you can bring in decision processes as well. We, within the research effort I did, was I just looked at task support, the support given to the sailors at the time, and then their overall capability, their performance capability and the performance of these tasks, and assigned values to those. So talking about small boat operations, because there's some background that's needed in order to look at this effectively, they routinely conduct operations in littoral waters. Littoral waters in this case means close to other ships, not close to other ships, close to shores where there's a high traffic density resulting in a lot of ships. So this was very similar to what the Navy saw within the PACOM theater within the 2017 timeframe. But it also fits into the small boat defense operations. And time is one of the key factors in that, and that critical time. So the critical time, if you see a small boat on the horizon and you identify that small boat may be a potential threat, you have actions you have to take in advance of that small boat being able to quickly approach your ship and potentially detonate or cause some other damage to the ship over the course of time. So how do you do that? You have to factor in the variance across the crew and provide them the tools and the training necessary to assure that they are able to meet that critical time limit. And then mitigating those crew temporal impacts is what we're looking for from that task support and capability and training. So what does that look like from a workflow perspective? Well, first of all, you have to identify or detect the small boat or the threat contact on the horizon. Once you do that, the officer of the deck or the individual in charge of the ship is going to give the order to verify the close-in gun, in this case, close-in gun system readiness, so that if you do need to use it, it is available. And once you have it identified as being available, you have to give the order to authorize the close-in gun system use. Once again, that's an officer on board that would give that decision. And then the gunner himself, once he's authorized use, makes the decision on approach when is the best time to remove the threat as the contact. So moving to the modeling environment now. So we talked about the systems engineering perspective and how you look at all the different roles and responsibilities. In this case, you had an event generator, produced a small boat. At that stage of the game, you had 3 watchstanders that could potentially see this. You had a lookout, you had a radar operator, and you had a fire control operator. Any of those 3 could have potentially detected it, and we assigned a probability that they would across that span of those watchstanders. Once you do that, there's communications involved. Communications to let the officer of the deck know that you have identified a small boat potential threat contact on the horizon, and then secondarily to that, the officer of the deck has to let the folks know out in the spaces to verify the close-in gun system readiness, basically putting them on alert that there's a potential threat contact out there. And then so after that, once it's verified correct, the watch officer will give the permission for the gunner to use the close-in gun system. Any of those 3, the 2 lookouts and or the radar operator or fire control could identify it. More than one could identify it, but every action takes place once the identification begins. So not having much experience in object-oriented simulation or agent-based model, I had to start with a basic building block diagram to take a look at what it would look like to me as an individual that was the watch officer. Having done this in a submarine, it was completely a different type of scenario, but the same kind of idea persisted. So you take a look at this from the detection, basically you use timeouts across the spans, and then I looked at 2 different cases because for dissertation research, obviously you have to look at an application of something that's never been done. It's got to be new and unique. So from that perspective, if you take a look at the case 1 and the data that's below it, you have the opportunity to see that they used a min and a max time, which is ultimately a triangular distribution. Well, Gregorides and Sutcliffe used a different approach to take in that human variability. They took the probability of low performance and the probability of high performance, or the probability of low task support or the probability of high task support, and then took that times, each of the individual times, to get a realistic human expansion of what the human variance will bring to the problem set. So now you can identify, okay, now that there's actual human variability assigned, am I ever going to exceed that critical time, as opposed to just looking at the subject matter expert derived triangular distributions. So once I had the building block diagram, and with some serious help from the AnyLogic staff and group here that responded to many, many questions, similar to others in that effort, I was able to go through and build each of those variant tasks and how they would look across the model. So I had the contact reporting integration where you have the watch officer, you have the lookouts, you have the fire control and radar. In this case, the lookout, once they would identify it, they would just go right back into being on lookout. But the radar operator and the fire control, they have subsequent actions they need to take after the contact is identified and you have the close-in gun system verified to be made ready. So that's the variance in the 2. The fire control and the radar state chart look effectively the same. So now the readiness integration, in this case, you had 3 different watchstanders that had to report back into the fact that they have verified their close-in gun system readiness, and each one of those will have a different temporal variance distribution that they use to verify that, again, system ready. They'll have different capability, different task support all across that spans. You also have the gunner that has to do it, and then the watch officer waits for those reports to come back before he can authorize the gunner to use the close-in gun system. And then ultimately the close-in gun system and the communications that goes with that, and then the time distribution of the gunner to actually fire the close-in gun system as he feels comfortable with the solution to eliminate the threat. So the data was the cherry on top of the effort with respect to, from a PhD perspective, we were trying to look at, was the triangular distribution and the Gray-Gerdes and Sutcliffe methodologies, do they actually result in different outcomes? And what were those outcomes and what were the impacts? So the key takeaways we took a look at there, we had the combined close-in gun system ready time and the contact ID to the close-in gun system firing. And you can see that on this one, the triangular distribution is biased to the higher end based on the function that you have 3 different watch standards with varying capability that take a look at the close-in gun system readiness. And the critical time was exceeded, the 40-minute critical time was exceeded in 806 of the cases. In these cases, we gave a capability to the sailor, the watch officer in this case, of 50%, because the watch officers typically tend to get a higher level of training, and they tend to stay in one spot on board the ship, one job format for quite some time. The overall sailors, we gave a probability of good performance of 30%, the rest of the watch team, because they tend to rotate through a lot quicker and don't have quite as much training along the way. All right, so that said, this is the Bayesian model that was Gray-Gerdes and Sutcliffe's use. So you can see in this case that the high capability assignment of 30% to the non-watch officer sailors result in a skew, a much higher skew to the higher end of the range. But it actually produced less variability because since it's now an equation instead of a 1,000-run Monte Carlo triangular distribution, you only have set discrete capability of times to come in. And the critical time was exceeded in 823 cases. So close. And so now the question was, is there a difference between the two? Also, we took a look at workload, and we wanted to identify, are we overtasking our sailors? Are we not allowing them the opportunity or the time to actually perform the functions they need to perform in order to eliminate the small boat as a threat? So if you take a look at the workload utilization, that's how much of the available time for the sailor was actually used during this scenario. And there's adequate time in the Bayesian model, but this was for a single contact. Didn't run it with multiple contacts because I was trying to look at the functionality of the Bayesian, Gray-Gerdes, and Sutcliffe solution to see if there was a difference and if it actually brought in more reality. A little foreshadowing here, it did, and there was. But all that said, with multiple contacts or multiple other tasks, which is usually the case on board ships, you are going to have to identify whether that workload utilization approaches and or exceeds 100%. Now you've overtasked your sailor and you're no longer able to rely on them to perform those tasks in the same time frame or with the same applicability as they could if they were within the workload utilization of 100% or less. And certainly we can use this same methodology resulting for multitask or multi-contact environments. So the total response time mean comparison, this is where you're actually looking, is there a difference between the baseline triangular model or whether you're looking at the analytical model total response. And the mean time response was about 43 to 46. So you do your standard assessment of the null hypothesis, and it did indeed prove that there are 2 different outcomes from the 2. So you can say that the Bayesian model used and created as a result of Gray-Gerdes and Sutcliffe resulted in a better and different discrete solution set from what you had just got from a triangular distribution. And then, so real world and sailor capability and influencing factors does adversely affect the temporal variability, total response time, and it provides a separate solution from what you would expect in a triangular distribution. And based on empirical data and sampling, it probably provides a more accurate answer. So what does that actually look like? Where's the break point? What do we get then as we invest in sailor training or capability? We took a look specifically at sailor training and their capability of performance. And you can see that obviously, and this wouldn't come as a shocker to anybody, that the more you invest, the better of a response that you get out of the sailors. But there is a break point right there at about between 70 and 80% where there's a knee in the curve, so to speak, if you were to plot the inverse of that. And so, as you assign what values you give, what metrics you give to your sailors for achievement or capability, whatever that is, that 70 to 80% break, your return on investment and training beyond that becomes smaller and smaller over time, and you might want to assess from a leadership perspective if that was worth the cost and the time or the man hours, et cetera. But certainly ship design, crew recruitment and training, and watch team architectures can be evaluated to affect the changes through a model very similar to this, and assignment of the correct metrics attached to that capability and that task support. And you can use that from initial concept and design all the way through your training and your actual ConOps development for your ships. We use the agent-based modeling to get to a realistic solution to evaluate a U.S. Navy operation. It wasn't the exact operation, two ships operating in close contact with one another, like we saw on the original slide. It was part of that Pacific Fleet memo. But it was very similar, and I had data available for this and could evaluate quickly and readily with the agent-based modeling and simulation whether there was an impact, whether it was a viable impact, and whether it provided a more realistic example. And then it did provide some potential information back to the Navy. This was put done as part of an Office of Naval Research project that they provided funding to the University of Central Florida for. And it does also add growing literature on the interplay between the physical and cognitive abilities, because you need the attention and the perception and all those other aspects that go into that cognitive ability before you ever have to worry about executing the physical abilities, because you have to be able to identify there's a contact, get that through the system and through communications and other facets of activity before you ever have to worry about taking the physical actions necessary to verify the close-in gun system readiness as well as the actual firing of the weapon system. And with that, I think I'm down to Q&A. Over there.
So you compared using a triangular distribution from subject matter experts to the stochastic Bayesian approach, but have you tried to validate either sets of those numbers by having the Navy track these actual response times in training exercises or in real life scenarios?
Validation with agent-based modeling is very difficult. Verification was pretty easy. Validation was something that covered the discussion many, many times. They actually had a case with a separate example where they built a warehouse, built it up as a ship model, and did multiple runs and iterations with sailors to identify whether they could validate some work they were doing at the time, and actually developed the triangular distributions. They seemed very focused on triangular distributions and trying to apply those. But the actions were so quick and so short, and the sample, although I say multiple iterations, certainly they didn't do it 1,000 times for like Monte Carlo statistics. This was done a grand total of 10 times. And with those low number of statistics, it was very hard to get any validation. I ran that through the model as well. It came close, but I wasn't able to verify that it was valid completely. But if the Navy were invested in it or interested in it, they could certainly do that. Yes, sir.
Have you considered effects of drills on the readiness?
Yes.
And that's where you could also get some data that the other colleague was speaking of.
Absolutely. The training evolution, the drills, multiple times a week, we all know they go through that. That's mostly what they do, and how they spend their time at sea is getting ready for the next big event that they have to be able to prepare and perform in a time critical perspective for. So from that aspect, that went into my overall assessment of the capability. The metrics I assigned, that 30% to the sailor capability, based on my experience, some additional conversations with Navy folks, and the amount of drilling I've seen they actually do on surface ships versus a submarine. So it was much more subjective, and there hasn't been data collected yet. But once again, if the Navy is interested in that, we can go out and do that very easily over time. And one of the ideas about this is that as the Navy moves to more of a computer-based human systems integration architecture, they can actually collect the data automatically without exactly having folks that need to sit there and tag it and time it and then put the data out.
I have another question. I'm a little confused because you use the term systems engineering and putting your work in the context of systems engineering. So how did you account for the soft aspect of systems?
The soft,
which is people. Yeah, well, you have
well, yeah.
Systems engineering is the hard element and the people is the soft. So how did you reconcile the two? Because you're saying systems engineering.
Well,
so what I understand from that is hardware based. How they
Yeah, and I think that's why I kind of kicked it off with the fact that it's human systems integration. From the fact of, from a systems engineering perspective, this was all a human systems effort. There was really very little with respect to mechanical or hardware of any type of activity at all. This was all about how fast does a human walk from point A to point B because you have to deploy your watch standards. What is the likelihood that they'll have the attention and perception and cognitive capability to identify and report this contact? This was actually a object-oriented simulation build, and I can actually go back a few slides, but an object-oriented simulation around the entirety of the human in the system, so much more than the actual hardware that was around the system. So each of those looked at the human perspective and the human response and the human capability from that perspective. It didn't look at what you would typically think of from an industrial engineering perspective or a systems engineering perspective as the hard components, but it was entirely a soft component look.
I know with the Department of Defense modeling, sometimes data can be hard to come by. I'm sure you know too as a Navy veteran. So what level of assumptions did you have to make either by yourself or with subject matter experts? And did you get any opportunity to try and create some of your own data?
Caveats and assumptions are a key to any dissertation, but no, there were a lot of assumptions, and I don't have the list up here. Certainly I can get offline and talk with you about it. There's probably about 30 assumptions that went into all this with respect to the fact that you had a reasonable sailor performance. You didn't have somebody off the sick or injured list delivering capability. You had clear visibility. You had sea state assumptions because obviously the variance in the sea state with the rocking of the ship and the ability of you can be range limited in visibility by fog, overcast, a bunch of things like that. So that went into that 40-minute critical time. Certainly in a much more overcast or foggy environment, your ability, other than with radar, and sometimes that's not very good in a fog-laden environment, to actually identify the contact at the right range in a much more lower visible, your critical time shrinks considerably. And what you'll do is you'll find that most Navy ships, they actually, when they consider themselves to be in a potential threat environment, even before there's a small boat there, they have all the watch standards on site and they have the gun system verified ready so that if they need to use it, they can, and that cuts a lot of the time out in advancing towards that critical time. But there's a long list of assumptions and caveats. Any other questions?
You just mentioned radar, but are there any other technology assists that could help with the detection and identification to make it either sooner or more reliable?
There are. Radar is probably the standard one they could use, but there are technology assists from CONOPS depending on what they have available to themselves from that perspective. If they felt they were in a threat environment, they could actually put up a helo to provide additional oversight and ranging to actually circle around the ship at different circular ranges of diameter to identify if there's any potential threat contacts out there. Radar is certainly one. The lookouts themselves. There are a few others out there. Coming from the submarine, that radar was the principal one we used. Any other questions? Well, thank you. I appreciate it.